So today we'll look at one of these faster algorithms and sort of the principles that you can leverage in order to do better than bubble sort. But first, a few empowering techniques. So thus far with problem sets and even lecture code, if you've been playing along at home, you will run into bugs, right? Your code might not compile. You might get segmentation faults or core dumps. Your program might never stop. And so it just produces output and output and output, or the cursor never comes back to you. There's so many ways in which you can screw up a program, and it gets easier, trust us, to actually find the problems therein. So thus far, if you've been debugging programs, hopefully you've realized that printf is absolutely your friend. Plugging in a few printfs to see what the value of x is, what the value of y is at this point and this point and this point can certainly help you along. But unfortunately, printf can only take you so far. Plus, it's tedious. Then you have to rip out that code once you found your problem. And especially now that we're in problem set 3, which is a game, the game of 15, there's a little bit of primitive animation there. And you're going to completely screw up the game board if you're trying to print out some error messages or the values of variables on the screen at the same time. And so we kind of need more sophisticated techniques now to debug programs. So enter into the picture a program called a debugger. So one of the most popular debuggers out there for Linux and Mac OS, and it's available on Windows as well, is a program called GDB, GNU Debugger. And what this program allows you to do is set what are called breakpoints in your program, whereby you say, don't run my program all the way from top to bottom. Rather, pause execution on line 13 of main. Why 13? Well, you're suspicious that you have a bug somewhere around line 13, but your program's flying by so fast that you can't really wrap your mind around what the problem is. So you'd really like to slow things down and look at step 13, then 14, then 15. Well, a breakpoint, as the name suggests, allows you to break at a certain point in your program, and then at your pace, your human pace, only advance line by line when you're ready. Similarly, while you're inside this debugger, you're going to be able to print out the values of variables. So you don't have to use printf. You can just ask the debugger what bits are inside of this variable x, what number is there, or what string is here. And so you can actually see the inside of your program while still interacting with it. So let me go ahead and open up the appliance here. And I'm going to go ahead and open up, let's say, a program called, let's go with about Buggy 3. So Buggy 3 was this program. And we'll actually finally start solving this program, this problem this week and next. This was that broken swap function whereby in main we had an int x and a y. They each had some values. We had some printfs. Then we called this function swap, which then looked like this. And we claimed verbally a week or so ago that swap was correct, at least insofar as it goes when it comes to swapping a and b, but it did not swap x and y. The moment swap returned, yes, a and b we claimed were swapped, but x and y were unchanged. They were still 1 and 2 respectively. So just conceptually, what was the explanation behind the bugginess of this program? Yeah? Yeah, so the values of x and y, the x and y were passed by quote unquote value, which meant a copy of x and y was passed into swap. Swap just so happened to call them a and b, but it could call them whatever it wants. But they're indeed distinct 32 bits worth of integers. So at this point, when swap was called, we claimed that there exists in this world x and y, and then also a and b. And if you think back to how we drew the RAM inside of our computer, main's variables were down here, this slice of the stack frame, so to speak. And then on top of it, somewhere else in RAM, was a and b. So just pictorially, too, they were distinct chunks of memory. So now we can finally see things like this. And this program isn't just, fixing this program actually takes a bit of ingenuity. And we'll actually get there later this week. But for now, we can at least understand what's going on and not just have to take my own word for it. And along the way, we can actually learn some of these commands. So I'm going to go ahead and do this. I'm going to open a larger terminal here just so we can see more at one time. I'm going to go ahead and run make Buggy 3. Okay, it's up to date, which means I already compiled it last week, so that's good. And I can go ahead and run it just to prove that it's still broken. So x is 1, y is 2. They're still 1 and 2 at the end of this. So let's now, instead of running this as Buggy 3, let's instead run GDB and then pass to GDB, as a so-called command line argument, the name of the program I want to debug. So I'm going to go ahead and hit Enter now. And now I see a bunch of warranty information and all this, and then a new kind of prompt. At the bottom left there is a prompt that says, in parentheses, GDB, and that means I'm inside of the debugger, and nothing's going to happen just yet. I can hit Control L to clear the screen. Now I'm inside the debugger, but my program's not running yet, but I can run it. I can literally type run, enter, and voila. I've run the program inside of a debugger. Now, unfortunately, this is not at all useful thus far. All I've done is now run my program inside of another program, but I haven't specified that I want to poke around. I haven't specified breakpoints. I haven't specified I want to see anything. So let's do that. This time, I'm going to hit Control L just to keep the screen clean. I'm going to type break. And I don't actually remember the line number, 13 I made up before, but I know the function name. So I'm going to start simple, break at the function called main. And what you see now on the screen is breakpoint1 at 0x804842D file buggy3.c line 21. So on the one hand, GDB figured out where main starts. It's apparently line 21. But what in the world is this 0x804842D, do you think? Yeah, so it's a memory address. And we'll start seeing more things that look like this. But almost any time you see a number in the context of programming that starts with 0x, first of all, that's indication of hexadecimal notation, or base 16. But we'll come back to that. But for now, it's just another way, like decimal and binary, of expressing numbers. And yes, that represents the address inside of my computer's memory at which what lives? Main itself, right? We said last week that main itself, and really your program itself, lives inside of RAM. In fact, it's one of the things that's up toward the top of your memory, and one of the things you run the risk of clobbering if you call functions way too many times such that you overlap that memory. But for now, GDB's figured out where it is. It's set a breakpoint, number 1. And now if I go ahead and type run and hit enter, now it runs, but it seems to break quite quickly. So it says breakpoint1 main at buggy3.c line 21. Well, I forget what that is, but GDB is reminding me. If you'd like to see it in context, you can go back to gedit, and you can scroll down and find line 21. If you've never noticed, in the bottom right corner of gedit, it always tells you what line you're on and even what column you're on. So you can do a quick sanity check there. So I'm going to go back to my terminal now. And GDB at this point is saying, you're on line 21. I'm about to execute line 21. What do you want to do? Well, let's go ahead and do this. Let's move on to the next line. So next means execute what you see and move on to the next line. All right, now I'm going to go ahead and say, yep, let's go ahead and execute this. Next. OK, now I'm going to get to line 25, and it's going to print out, it seems, the value of y. Well, what is this? Why did it do that? Interesting. Let me go ahead and do this. Print y, enter. So is that consistent with what we expected if I go back to the code here? So yeah, y was initialized to 2 here. I'm now down at this line here. The reason I'm kind of mumbling to myself is I'm actually not sure why GDB just skipped x there. So we'll come back to that later. But for now, we're at this line here where y is %d. If I print out y within GDB, it is in fact 2. So let's hit next again. And now, indeed, it prints out as much. And now let's go ahead and say next. And oh, this is interesting. This is the line of code that, if executed, is supposed to swap x and y. So quick sanity check. Let me go ahead and first print x. It's still 1. Print y. It's still 2. As an aside, the $sign notation here, this is just a GDB thing. It's giving you temporary nicknames for those values in case you want to refer back to those values. But for now, you can essentially ignore the $2 and $3. All we're seeing now is the value of x and the value of y. All right, so let's go ahead and hit next and let swap do its thing. So I hit enter. Now it's about to print out swapped, exclamation point, but let's do a check. Print x, still 1. Print y, still 2. So clearly, it's broken here. So let's start this over and actually see where the problem is. So let me go ahead and type run again. It's going to say, wait a minute, you're still debugging. Do you want to start it from the beginning? I'm going to say yes. And now we're back at the beginning. So now let me go and do a sanity check. Print x. Ooh, seems like I've got multiple bugs. What's going on here? Sorry? Yeah, so I haven't hit next yet, which means what? Line 21 has not yet executed, which means what should be the value of x? Right? It's some garbage value, right? We talked last week about how because these stack frames are always piling up and going down and up and down, you're reusing the same bits that some other function, maybe not even written by you, has actually previously used. So what we're seeing at x's location is this number 3,219,444. Those are just random bits left over from something else's execution, and so we're just seeing the remnants of that. But if I do click next and then print out x, OK, phew, it's back to 1. If I print out y, same thing, another complete garbage value. But if I hit next now and then go ahead and print y, now it's back to 2. So let's hit next. Let's hit next. And notice it's just doing the printfs. And this is printing correctly. I must have hit something wrong earlier. So let's hit next now. And now swap. So if you want to step into a function and not step over it, what you do instead is literally type step. So if I type step, now notice what GDB is telling me. I'm now inside of a function called swap. The arguments that were just passed to this function are 1 and 2 for the variables a and b respectively. I'm at line 41 in the same file, buggy3.c, and I'm about to execute line 41. So let's go ahead and do this. So let's do next. Let's do next. Let's do next. And now line 44 is the curly brace. So this is where our story verbally used to stop. Let's do a quick sanity check. Print A, print B. And what should temp be if I print temp? 50% chance here. And it's indeed 1, because we initialized it to the value of A and then used that to put the same value in B. So this looks right. When I printed A, I got 2. When I printed B, I got 1. So let's go ahead and click Next. And now I'm back. GDB is telling me back in main where I left off, line 28. So if I now print out X, print out Y, they're still broken as we expected. And if I try printing A, no symbol A in current context, print B, same thing, because they're no longer in scope. So to be honest, using GDB, even for these simple operations of using print, next, step, and break are hugely more powerful than just using printf alone. So we'll spend time on these in section and certainly more over time as well here. But if you go in the meantime to cs50.net/resources, you'll see that under the GDB tag, there's some documentation here, but there's also a little quick reference cheat sheet that has way more commands than you'll probably care about initially, but it's a one-page PDF you can print out, and it's a cheat sheet of sorts. And you'll see that it gives you a quick sense of the various commands you can type. And also, GDB is nice in that you can be fairly succinct. You can just say P for Y, P, X. You can almost always type just the first 1 or 2 characters of the command, so you don't have to redundantly type out print all the time. And you can also scroll up, down, left, right. And finally, when you're done, just type Q or quit, and that will warn you that you're about to quit. And now you're back at the appliances prompt. So a hugely useful tool. And this is one of those things, honestly, where I did the same thing. We sort of introduced this. We claim that it's incredibly useful, but there's invariably a learning curve, whether it's 10 minutes, an hour or so to acclimate to it. And so this is absolutely one of these tools that like almost every student puts off, myself included back in the day, until later and later and later in the term. But honestly, spending the 10 minutes, the hour for PSET 3 and 4 to play with GDB, I promise will save you hours of time in the future. It is so much more useful than just using printf in your own brain sometimes when looking through code. It allows you to step through much more reasonably. All right, any questions on debugging or GDB? Yeah? Good question. If you're dealing with arrays, by default, GDB will usually know how to print something that's like an array or a string, which is an array of characters. It does sometimes depend on the context. But for now, if you declare an array inside of a function and then type print space foo, where foo is the name of that array, you should see all of the members of that array, yes. The only problem arises sometimes if you start passing that array around, which we haven't really done except in problem set 3's distribution code, that sometimes GDB essentially loses track of the length, and so it has trouble printing it for you. Other questions on GDB?